So the name for our group is Adaptive Agriculture System. And you can go to the next slide. They're just our outline. You can go next. These are the team members. I'm Daniel Echevarria. I'm the project leader. I'm basically going to be working on the integration between the software and the hardware design, as well as the plant information for the database.
Hey guys, I'm Mark. I'm a computer engineering major, and I'll be working on the software design as well as the user interface for the touchscreen.
My name is Steven Guamin. I'm an electrical engineering major. I'm in charge of the plant data manipulation, the sensor integration, as well as the hardware design.
Hi, I'm Michael Isella. I'm a computer engineer, and I'm in charge of the database design and implementation.
So our main goal was basically just to make agriculture something that's achievable in any kind of home. We wanted it to be easily accessible and user-friendly. When we were looking at like our research and trying to pick a project, we know that like with the current state of events in the like environment and things with like wildfires and stuff like that, it's like a big push to get green solutions going. And on top of all of these environmental issues, you also have like shrinking cropland, increasing prices for crops, and with all of these things compounded, we thought it would be a good idea to make food just more attainable for everybody. So when we looked at like some other existing products, there's a few things that they hit the mark on what we wanted to achieve, but there's some things that they were missing. So we tried to combine all of them into one. The main thing was we wanted it to be affordable, easily accessible, as well as practical to use. So when we look at like these three examples, these are probably like the most aligned with what we wanted. The Click and Grow is the first one on the bottom left. It's like a tabletop. It's practical, you can put it anywhere, but it's limited in what it can grow. When you look at the Planty, it's simple, it doesn't have any sensors. It's kind of just like a box with dirt and seeds, and you track it yourself. And then as far as the Biopod goes, that aligned the most with what we wanted to do, but it was really hard to get your hands on one. I didn't see any shops that even like sold them. And two, it wasn't really modular. It kind of defeated the purpose of like the whole adaptability and like green solution thing. So basically, as far as like the hands-off things goes, it's going to be using a lot of like water sensors and light sensors in order to basically monitor the condition of the plant. That's why we named it the Adaptive Agriculture System. The whole point is you put the plant into this enclosure and monitors the conditions of the environment, of the enclosed environment. And based off of that, it disperses the nutrients or resources that the plant needs. The only time the user should have to interact with it is when the water is out or the light messes up or something like that, or once they actually want to reap their crop. And then as far as like a societal impact and like the global impact, like I said, it's like a green solution. I think in the future, it's going to be like having some kind of like self-growing system is going to be as common as having like a washing machine or a dishwasher in your house. With everything that's going on with like food prices recently, it's kind of obvious that vegetables and fruits and berries, all of those things that grow out of the ground, as cropland continues to shrink and become more expensive, is going to translate over into these vegetation prices. So we're trying to see ahead of that. And specifically in like disenfranchised areas, it would be nice to be able to grow your own vegetables, even if it's not something that can feed an entire family. The idea is to take some of that pressure off and provide some kind of food, at least for a little while.
So our design requirements were broken up into marketing and engineering. So for the marketing, we wanted it to be easy to use for every user of every level and have the touchscreen layout be a clear overview of all the operations. We didn't want it to be too expensive for the entire system so anyone could use it. We also didn't want the whole system to be too large to obstruct the room that it's in. And we also wanted all the components to be easily accessible if a person needed to change or repair the parts. And then for the engineering requirements, we would need a closed chamber with ventilation gaps to allow the byproducts to flow out, an efficient touchscreen to automate the watering and light. We need it to be battery operated with a wall plug-in also. The water pump will be 5 volts to automate the water. The LED lights will maximize the energy output with minimum power. And for the estimated dimensions, we want it to be about 4 feet tall and 2 feet wide. And with full water, the soil, and a plant in it, we don't want it being bigger than 50 pounds. And this is just a summation of the previous 2 slides. So the up arrows mean positive correlation or strong positive correlation, and the down arrows mean negative correlation or strong negative correlation.
And then this is just our related theory. Since our system is really just like a monitoring system, an automated system, the real like theory behind it, it has to do with the light sensor, which is like basically the photodiode sensitivity, and the moisture capacitive system. Basically that it's just like a metal rod with a coating on it, and based on the environment that that device is in, it can detect the capacitance. And basically the capacitance is that formula right there.
And for the planter itself, it is going to run every 30 minutes or so. It's going to run a check on both sensors, the light and the moisture. And we'll take those readouts, check them against the database that we're going to implement in there that's going to have all the plant values. And if there is any difference between the 2 values, it'll decide whether or not it needs to turn the light or adjust the lights or turn the pump on. The pump will be set to run for a certain amount of time based on the difference in the values. And then once it runs through the whole process, it'll take another 30 minutes until it runs another check. Here we have a very basic model that I put together of what the planter is going to look like. There's going to be a top chamber with a removable lid that is going to have all the hardware in it to keep it away from the water and the dirt. The central section is going to have 4 small planter sections to allow the plants to be in there. The bottom is going to have a drawer that will house 1 to 2 water tanks, based on if you want to have a tank with nutrients in it and one without. And then the central support beam in the planter is going to be hollowed out as to make it so that we can move all the wires through it. And here we have 2 flowcharts for the software that we're implementing. The database, it'll, on the touch screen when you access it, it'll print out the list, and then you'll have a few options to add a plant to the database, remove a plant to the database, and change certain plants' values if you notice that it needs to be adjusted.
And for the touchscreen flowchart, basically it just draws the home screen in a loop with nested if statements. So there's 2 buttons for the lighting and 2 buttons for the watering. If those are pressed, it turns it on. And then there's also a settings button in the top left corner. And if that's pressed, it draws the settings page.
And here we have a couple of demonstrations of the database and the touchscreen. The database currently is implemented on the touchscreen, but here I am just adding a potato to the database with some basic values. Then it reprints the list out with the new plant on it. Then you could also remove, which I'm showing here. And now I'm changing the individual values of the carrot in the database and showing that you can access all this directly and adjust it if you need to.
And this is just the touchscreen. You have the lighting buttons on, off, the watering buttons on, off. There's also time and date in the center, and then the settings page.
For the circuit schematic, I use the Arduino Uno. Since we're using a 5 volt pump, we can get the voltage supplies directly from the Arduino. So the blue wires are the inputs that the Arduino is receiving from the soil moisture and from the relay. And the red wires represent the supplies that we're getting from the Arduino, which is 5 volts for the relay and 3.3 volts for the sensor. So here we can see the soil moisture sensor equations. And in our system, we're using a resistive soil moisture sensor, which basically works by using the relationship between the electrical resistance and the water content in the tank to monitor the moisture levels of the soil. At the end, our soil moisture sensor has two probes which go directly into the soil. So the electrical current is sent from one of the probes to the other, and this compares the resistance between them. So when the water content in the soil is high, this will produce a higher electrical conductivity. So this results in a lower resistance, which would indicate a high soil moisture. And when the water content in the soil is low, this results in a poor electrical conductivity. So this reading would indicate a low soil moisture. And since I use the Arduino Uno, I use the Arduino Uno IDE for the software. And here we can see a basic flow chart, which basically takes the input from the soil moisture sensor, and that triggers the relay to turn the pump on. And then there's a small delay when for you to insert the sensor into the plant or whichever vegetable or fruit you're gonna grow. And once the sensor gets placed into the soil, it will display the moisture levels on the Arduino Uno IDE. And for this example, I use the threshold moisture level of 750. So if it's above 750, the pump would be off. And if it's below 750, the pump would turn on. So here's a demonstration of the pump working. So we can see there's the Arduino Uno connected with the relay and the soil moisture sensor, and the water tank is placed on the bottom. So here I'm connecting the Arduino to the computer so it can power. And once it gets plugged in, the water will start to flow. And once I insert the soil moisture, it goes down and it stops pumping. And once I lift it up again, the water starts to flow again. So it's reading that the soil moisture is high. And here's the moisture level on the IDE. And here's basically the graphical results of the test. So we can basically see the pump being turned on and off. As we can see, the moisture level goes all the way up to our threshold, which is 750. In this case, I went a little bit above, like about 850, 900. And that instantly turned the pump off. As we can see, the really the drop, the instantaneous drop almost once it reaches that threshold. So that indicates that the pump is working as expected.
And here's the project schedule for this semester and next semester. So far, we've been able to hit all our deadlines that we wanted to. So now we are going to, over the break, continue to work on the project and start to grow some plants that we can put into the planter itself to run some continuous long-term tests towards the end of the next semester.
And then this is our just bill of materials. We have the board, the touchscreen, the LED lights, which is like a ring, our moisture sensor, the valve, the tank, and the seeds.
And so now that we've come through this semester, we have been able to properly make some realistic goals for ourselves. We know how well we work as a team. and we know what we need to do for next semester to make sure we get this project finished in the best way possible.
So there were just a couple of basic standards that we used. The USB 2.0 interface was to connect to the Megaboard or the Uno, whichever one we were using at the time. The I2C bus was used to communicate between the touchscreen and the board. And lastly, the JDEC JESD87 was for the water pump and the battery. And then ethical issues. So our group applied a conditional rule-based ethics to the project. We wanted our project to be unique to us, and we didn't want to copy anyone else. So we act as if we were applying for a utility patent, following the requirements of keeping it novel, non-obvious, and useful. And then another rule we applied was splitting the work evenly between all our team members. So we didn't want to put all the work on one team member and just bombard them. But for if an unexpected and valid reason one member fell behind, then the rest of the team would pick up that work just to keep pace with the schedule. And the rules incorporated by our group served in addition to the IEE Code of Ethics. And for complex engineering, obviously our project was based on the disciplines of electrical and computer engineering. And then mostly for next semester, when we're building the planner, we'll have to go to the mechanical engineering department to use the 3D printer. The chemical engineering, for the soil moisture, it monitored the chemical properties in the soil to automate the watering. Computer science for the touchscreen and the database. And then lastly, psychology. We wanted our product to look nice, and we wanted users to want to buy it.
Yeah, that's everything.
And that's everything.
Any questions for the group? Okay, thanks everyone. And now I would like to welcome Dr. Manai to present her students.
Thank you, Dr. Sultan, and great job, Michael, Stephen. The project is very impressive. So I would like to, you're welcome. I would like